Okay, we will get started. Any questions for the homework? Yes. Yes. True, yes. Yeah. And especially saying you have some choices. For each of choice, there is sort of a obvious solution. What you choice of different levels, you can how much 世纪有升级拿对了。Not there's no strategic thinking. Sort of you list what kind that you'll be very sensitive to the demand curve. So the demand curve changes a little bit, right? The conclusion will change. That's sort of the goal of that problem. Inequality constraint. Exactly. Something less than zero. Right? You have to write it that way. So you cannot bring the 10 to the left-hand side and think this is greater than it. That doesn't work. That's science. So this has to be less than or equal to sign. So we did not handle greater than equal to. You have to flip the sign somewhere else, but to be consistent, make every inequality less equal to something. Okay. Otherwise, sort of the solution doesn't make sense. Okay. Right. So that's the point with that question. From last class, we're looking at the power, active power, real power. So if you recall, what we wrote was that it's a function of time given the voltage. Sine to omega t. Your active and reactive power, right? So you will interpret the first term basically as some power that's going from the source to the load. You interpret the second term as the power that goes back and forth in your system. Okay. So we'll give this a name. We'll call it. Whenever you see P in power systems, that does not mean a time varying power. Time varying power is almost never used in power systems. So if you call active power P for power, then for reactive power, you just call it Q. Just call the other thing Q, right? So again, active power is a power that does work. It flows from source to sink. Reactive power is a sine wave that oscillates between the generator and, let's say, an inductor. That's the oscillation you have in the system. Okay. And we can define, of course, so everything we do is in terms of, right, so if you look at active reactive power, what you have is, let's look at the units on this actually. So this has a unit of watts, kilowatt, megawatt, and so on, right? So this is normal, this is power. Anybody know the unit? Volt ampere, right? So what the thing to remember is you cannot give a unit of watt. Or heat up. So we don't give a unit of work. So what you do is we basically give it a very descriptive name. We call it a volt reactive. Okay, that's a unit comes from Q. And you have voltage, right? There's V times I, so it's a volt, amp, and R denotes reactive. So you have something like, V have kVA, kVAR, you have, so that's a unit for different units. Again, when you pay for power, you pay in terms of watts, kilowatts, megawatts, and so on. So in power system economics, Q is really for system economics. Q is not often. Okay, so it's there, it's sort of there with most often there. Okay? But so the calculation is sort of much simpler than this. Well, the calculation is the following is you don't need to write out this in the time domain. What you can think of is you have voltage as a voltage phasor, right? There's some voltage with some angle and with some magnitude and angle, theta V. Theta I. Okay, so that's how we think of a complex power, right? So we think of voltage and current as complex numbers, there's some magnitude and some angle. Okay. So what we can do is you can compute the complex power P and Q through the following formula. So we define something complex power as V. So I'm going to write a bar for complex number. Right? So this is star means conjugation. Star just means you conjugate the complex number. Okay. Why the star is there to make sure this gives you the time domain definition. Okay, star just there such that the equations make sense. Okay, so you have to conjugate something. We conjugate the current. Okay, it's just the way that equations works out. Okay, so it's very important to remember this conjugation. But there's really not a sort of that deep of a reason why you have to conjugate this. It's just the equation works out. So what happens? What happens if you conjugate this complex number? What's the conjugate of that? Right, you flip the angle, right? So the magnitude stay the same, you flip the angle, that's the conjugation of a complex number. So here you get V, so this, the angle changes, right? So this is VI, theta V minus theta I. In Euler's formula, this is VI plus JVI sine theta. power, right? So complex power is just a way to compute P and Q. This is a shorthand formula compute P and Q. Questions about this? Through this formula, you observe that angle no matter, only the angle difference shows up, right? So through this what formula tells you. Why is that? Sine wave. You can pick the starting point of sine wave anywhere you want. All angles are reference to something, right? So there's no notion of that's actually the key thing to remember. Power flow. Angle, but the angle difference. So this is similarly how voltage drives current flow. The current that flows only depend on the voltage, not the absolute voltage, right? So the similar as voltage, angle is very similar to voltage. There's no absolute frame. You can pick anything you want, okay? So only the angle difference matters. So this is we have two sine waves. What determines how much power gets sent is the phase offset between the sine waves. Again, not the absolute angle. Okay? This actually has sort of far-reaching consequences in power. But for us, I just think to remember that you care about the angle difference. So often for complex power, what we do is we think of, right, so what happen is you can shift one of the angles to be zero. Okay, since only the angle difference matters, normally you take the voltage angle to be zero and say the current has some angle minus theta, where theta is the angle difference. Okay, so you get a slightly cleaner formula. All right, any questions so far? Okay, good. So now let's keep reducing this. So this is still a complicated formula to use. On a simpler formula, we have something called small angle approximation. Okay, so small angle approximation is saying that this equation is not a very good equation because it has something multiplying something. V is multiplying I. Not very nice. Has a sinusoid, cosine, sine in it. Not very nice. Okay, not very easy to use. For example, it's not very easy to solve the equation in this form. So what you want is you want to make this equation sort of simpler. And we'll go through the typical steps that makes this equation simple. Okay. All right. So if you look at so there are several steps to get to this. Altogether, they're called a small angle approximation. So the idea is, let's first look at the transmission line. Okay, so transmission line is the line you see outside, right? So there's, this is your transmission line. Okay, and so there you have, on the poles you see the transmission line. So what is the circuit equivalent of a transmission line? If I want to model this as a circuit, what do I get? Right, so this line is a physical line. Of course, when we do this calculation, we have to have a circuit equivalent model to this. So what do you model this line as? Right, so let's do this slowly. Let's do the capacitor branch, right? So let's say the true model is the following. Insert the circuit model. You have a capacitor okay, so this is what the line looks like. Anybody remember where this comes from? Not really. So anybody remember how we derived this? This is so-called pi model for people in power systems. It's our famous pi equivalent model. Anybody remember how this is actually solved? Close, close. Okay, yes, and you can do a Laplace transform. Where is the sort of physical basis of this? Right. So have people heard of the telegrapher's equation? Electromagnet is what you say is you have this line, you have any conductor. What this is made up of an RLC element. Infinitesimal small RLC elements, you chain them together. This comes from that. You think of this as a if you solve telegrapher's equation on this, what you get is because this is power system, you very quickly get a standing wave because there's no propagation of waves. You can almost instantaneously you get a standing wave. If you get a standing wave, it's as if the standing wave came out of circuit like this. So it's not really a grounding effect. It's just you solve telegrapher the differential equations. If you get a standing wave, the standing wave comes here. And you can find these parameters based on the length of the line and so on. But this is a true circuit model. Okay. Economics people and power system people are, for us, this is way too complicated. Anytime you see capacitors, not very good. Okay, the shunt branches is way too complicated. Okay, so what we assume is first, we're going to assume the capacitance is small. So are so roughly open circuit. So this assumption is not very bad. This is true normally for a line, let's say less than 1,000 miles. Okay, so for short lines, this is not terrible. Okay, so this is the assumption we make. So the capacitors are small. So that's capacitors are not there. So you get this line, right? So you get this line. Okay. There's still two elements here. You have a resistor and an inductor. So still not very nice to work with. There's still two components to this. So now let's look at this and think about it. Let's think is which of these can I get rid of? Can I get rid of the resistor or the inductor? I want the line to just be one element. That's the easiest to work with. So which is smaller in this? For smaller? Thing is not good. Thing is not good. You don't want to be safe. And this, so in AC transmission, what you have is you have a skin depth anyway. So AC power gets only transmit along the skin. So it doesn't matter how thick your conductor is, right? Because thickness of conductor has very little to do in AC power transmission. You're constrained to skin effect anyway. Right? So, that's not, it's really not the fact that you have sort of thick conductors. So this resistor is small because we transmit power at very high voltage. So the reason we transmit power at very high voltage is to minimize the fact that you have a resistor, minimize resistor loss. Okay, so that's why we transmit things like kilovolts of power. Okay, so you have a metal conductor, there's still resistance there. There's still some resistance. But what you do is you try to minimize this resistance. So what conductor actually looks like is you don't transmit power through a very thick cable. Again, because of skin effect, there's only this very little sort of piece that actually carries current. The charges in the middle of the conductor didn't do anything. So anybody know how we actually build a very sort of high voltage transmission line? Right? So one big cable limits, if things only happen in the sort of surface anyway, what do? Is you build many, many little cables, you bundle them together. Okay, so how we actually build it is what you have is you have a core. This core doesn't transmit power. This thing provides tensile strength. Let's make sure your cable doesn't fall down. And when around it, you build sort of very little small cables, things like this. You build a lot of small conductors, and along the small conductors, you transmit power, you transmit current. So skin effect is not very easy. You minimize the impact of skin. Okay. So your actual cable is you have there's some center cable that's sort of typically steel. You wrap conductors, you very small bond of conductor around it. So this minimizes the resistance. This inductor you cannot get rid of. Okay, there's no way to get rid of inductor in the cable. It's just there, right? This inductor. Anytime you have current flowing in a bunch of conductors very close together above ground, you will have inductance. Just sort of anytime you push current through something, you have inductance. So inductor you cannot get rid of. So let's get our resistor. So this is roughly inductor. That's our line. What transmission line is roughly an inductor. So let's say this has the reactance of Jx. So now let us compute the power flowing on this inductor. Okay, so we're basically trying to get as power as roughly like current. Angle is roughly like voltage difference. That's the idea we want. Okay, so let's say this is our inductor. Let's have V1, theta 1, V2. I want to understand this power going from 1 to 2. Okay, so I'm transmitting. Okay, so I have some voltage, V1 theta 1, some voltage V2 theta 2. Through an inductor, how much power do I get going out of one? Right? Okay, so because there's no resistance, there's no power loss. Right? This P cannot go anywhere else. Whatever comes out of one of them has to go in the other. Okay, there's no resistance. Q you can lose, P you cannot lose. Okay, so let's compute this. Right, so let's say the current. So what's the equation for current? Right. So the voltage difference divided by the reactance, right? That's the whole point of doing this kind of complex variable. Jx, right? So this is what you have. Okay, good. Then what we do is we have power, right? So the complex power S as V1 angle theta 1. Figure out the current. That's just what we have. Okay. So let's write this down. This is V1 theta 1, V1. Right, so you just conjugate every complex element, right? So you conjugate the angle. If you say a J, you flip the J. You multiply this out. What you get is you observe you have 1 over x sine theta 1 minus theta 2. So this is your P term. If you multiply this thing out, you sort of formula. What you observe is you have this thing, sine plus theta 1 theta 2 plus J. So this is your reactive power term. This is J over x V1 squared minus V1 V2 cosine. Theta 1 minus theta 2. Okay, so this is your other term, right? Okay, so we get this. We get S, and so we get the complex number. The first part is P. Q. Okay. So next we're gonna say is this is economics. We care about how money changes hands. Let's not worry about Q. Okay, it's not that Q is not there. We're simply ignore the fact that we have Q. I mean, it's like forget about Q. So ignore Q. So we have P equals to sine theta 1 minus theta 2. Okay. Good. Okay, so we're sort of much simpler equation now. But still you have a sine term. And the sine term are not very nice to work with. So what's the approximation here? Write out sine. What's a classical approximation of sine? Right? Sine x equal to x. Right? You have Taylor expansion of sine. You have x minus x cubed over 3, this kind of thing, right? So you're going to assume that sine x is roughly x for x small. So p is roughly theta 1 minus theta 2 over x. Shall I not confuse you with both x's? Z for z. So just the power flux between between a line, the power you send is proportional to the angle difference across the line. Okay, good. Yeah. Yeah. Well, we never do a time domain form. There's no time domain. Our power, the average power, right? So if you look at the time domain definition, time domain, right? We're gonna name the coefficient of that thing in front as p. The other coefficient as q. These are fixed numbers. They don't depend on time. There's no dependence on time. So there's no time domain, right? So after this, so from now on, forget the fact that time domain ever existed. All we care about is phasors. Okay, there's no time domain stuff in power. Okay, so any other questions for that? Okay, so this is called a small angle approximation, namely because of this step. Okay, this is you assume the angles are small. So anybody know how small the angle is in practice? So angle you see across the power transmission line. Focus on some power system. So this approximation is not too bad. In actual systems, most likely your angle is below 10 degrees. It's very rare. We don't want to operate a system where the angle is more than 10 degrees for many, many reasons. But normally the angle is less than 10 degrees. And for this thing less than 10 degrees, this is a very good approximation. So for 10, so for basically anything less than 0.5 radians, this is a very good approximation. So 10 degrees definitely works. 10 degrees is very good approximation. So this is true. So what does this tell you? How you should think of power flow? You should think of power as basically theta 1, theta 2 x. This is exactly the same of how current would flow if you have theta 1, theta 2 as a voltage difference and x as a resistance value. Okay, so everything you learn about current dividers works. Okay, so power is divided exactly like current. Okay, so same thing here, right? So later we'll see this kind of division. Right? So you have, let's say, two things in parallel. Okay, you can have, you can ask, if I send over P here, how much is P1? How much is P2? Exactly works as if you have a current and you have two resistors that divide, right? So the division is exactly the same. Okay, so from now on, pretend power is current, reactance is a resistor, do current division. Okay, right? So as a review for current dividers, let's I have some resistance here, I2, R1, R2. How does the current divide? Namely, which path does it go? The current go to the smaller resistor or the bigger resistor? Smaller resistor. So that's the thing to remember. We do this kind of division. Always do a sanity check. The sanity check is power or current should flow through the branch with a smaller reactance. Okay, that's a sanity check, right? Otherwise, it's easy to get confused which one does it go. But at the end of the day, you should check. That's mostly policy path. Okay. Okay, good. So this is the idea. So from now on, we'll look at the parallel path in power flow. Okay, so if I'm sending power from 1 to 2, there's two paths, one with different reactance, then flow will divide through right, exactly in this situation. This is exactly the same thing. Okay, so this will divide proportionally on the sort of ratio of the reactance. Okay, so now that's basically the idea. That's the idea. Once we get to a sort of three cycle network, it can get a little bit complicated. Always remember all we're doing is current division. We're doing sort of basic circuit current divider analysis. Okay. Right, so parallel path is actually not uncommon to see in power. We have a lot of parallel paths in power. Okay, so the reason for this is when you build, when you build a transmission line, okay, so this is actually a good, this is a good example of the following. So let's say you have a transmission line from 1 to 2, okay, and it has some limits, right? So it can carry a certain amount of power. Now you say, I want to double the amount of power that can go from 1 to 2. Okay, I want to double the amount of power can go 1 to 2. What you do is you build another transmission line parallel to it. The reason it doubles is actually you halve the power. There's a power division here. Okay, so normally when you build parallel lines, what happens is power divides. Each of them can carry more power. And the exact division depends on the reactance of the line. So this is our current divider. So for this, anybody remember the exact formula of the divider? How much goes on top, how much goes on bottom for the sun division? What is the ratio? Right, so I have some P, something times P, right? So I'm sending P over the two lines. This reactance XAXP. Anyone remember the formula of this sun division? Right, so the most thing to remember is this is XB over XA plus XB. This is XA over XA plus XB. So again, the thing to remember is the amount that goes on A is proportional to the reactance on B. The amount that goes on B is proportional to A. Again, power prefers the path of least resistance. Okay, so if XA is very small, XB is very large, you go with this A path. So it's XB over the sum. Right? So if XA is very big, XB is very small, you go the bottom path. Okay. So this is again same thing as current divider. Okay. So the thing to remember is the very common mistake is to say this is XA over this. That's XB over this, right? So that's not true. Okay, just remember the formula. Questions here? Yeah, so FA is the amount of power flowing through the pathway. Okay. What is PA? We want to call this a flow. So we use F for flow. Right. So you see, because you want to imagine as a power flowing. You don't call this, so you can call this P1, 2. You also see this. But if you number this as A, B, C, D, you see C is much more common. Yeah. Okay, so P is for sort of the total power injection, F is for flow along each line. Okay, so parallel path. Now the interesting comes is, so for the top one, that's a formula. For bottom one, this is more interesting, where you have three paths, right? We have this sort of triangle. Now the question is, how much does each of this flow? Okay, they still have to satisfy this kind of relationship. Again, there will be a power divide. All these paths are power dividers. Okay, so we need to basically do this calculation for three of them, okay, for three bus. Right, so all of this is done basically using the idea of superposition. Okay, so this is basically how do you superimpose different flows on this, and then flows can add and subtract and so on. So you can do algebra on the flow. Right? So the key thing to remember for this is basically if you flow, so let's say you have B, you want to send power to Y. Okay, so let's say you want to send generator B to load Y, maybe because this is the cheapest, B is the cheapest generator. Y wants to buy some power, you want to send from B to Y. Okay. Anytime you send power along this line, some power has to go here. Okay, so that's remember from Kirchhoff's law. This is again Kirchhoff's voltage law. Right? Voltage difference drives current flow. So here angle difference drives power flow. Some difference has to go here. So when you send, let's say 400 megawatt from B to Y, you have power will flow around all the paths. Okay, so typically power flows along every line. So power between two nodes typically involves power flow okay, so every line will happen. If you want to sell some power from B to Y, everything has to flow. Right? There's no way to avoid this. Okay, so just the fact of nature. Again, this has caused an uncountable number of political issues. For example, if you look at Brexit, right? So Great Britain said, I would no longer want to be in EU. Sure. But somebody has to submit, they buy power from EU. And then says, okay, I want no power to flow between my branches, but I still want to buy power from EU. Then there's a document saying that's not possible. You have to allow power flow. Okay, but then it gets very complicated sort of politically. But physically, the reason is physically power had to flow. Okay, and similarly in the U.S., there was legislation in Montana that said every power that flows through the state of Montana cannot be renewable. We don't want renewable power. We want fossil fuel generation. There's no renewable power that can flow through the state of Montana. That went up to a judge, and the idea was, well, there's no way you can tell. You have electrons flowing through your lines. Everything that happens in the United States actually impacts you. So good luck enforcing this law. Okay, so you do have this kind of thing come up. Just to remember that physically, this always happens. You have power just flows where it wants to go. So not much you can do about this. Okay. So if you have this kind of flow, then you have sort of different flows from one direction to another direction, and you have all types of, let's see. So let's compute this power flow in more detail. And so here, let's say I have this branch. Okay, so here, let's say I want to flow 400 megawatts. Okay, so let's say I want to send 400 megawatt from here to here. And let's see what happens. Okay. So I want to transmit. This is B, this is Y, send 400 megawatt from B to Y. Let's put on some reactance to the lines. So let's say this line is 0.2, so X of 0.2. Let's say this line has X of 0.2, X of 0.1. Okay. Let's see, these are the reactants on the lines. I want to send 400 from here to here. Now the question asks you, how much power goes here? How much power goes here? So let's say this is F of 1. So it goes this way, comes down this way. Let's say this is F of 2. Okay, so how much power? Consistent with the book. F1, F2. So I want to compute what is F1, what is F2. Right? So how much power goes along different paths. Okay. Any questions? Okay, so how do you solve this problem? I claim this is very similar to the parallel path vacuum. Right? So again, you're dividing power along two parallel paths. The power ends up at the same point. Okay, so dividing power at the same parallel path. So you basically have two paths, right? So what is, right? So you want to look at what is the total reactance along path one? What is the total reactance along path two? Again, reactants are like resistances. If you have point 2, go through point 2, then point 1, you add, right? You stop. This is there's nothing weird about this, right? So you stop. So F1 as you compare, this is, remember, this is x2 over x1 plus x2 times 400, right? You want to say what is the other passes reactance divided by the total reactance. So here you have this is x1 over x1 plus x2, 400. Okay, so this is 0.2, this 0.3 plus 0.2. Okay, so this 0.3 comes from summing this 0.2 and this 0.1. That's where the 0.3 comes from. Okay. Any questions? Maybe you're doing a lot of this. Like later in class, you'll be doing a lot of this. Okay, good. So this this is not a graph. This is not a graph. This is just a two wires connect together. Think of this way, just drawing where two wires come together. Right? Yeah. So none of this are a graph, right? We're not drawing graph. When you think of this, this is again called a bus. You want have something in your mind, think of I have a wire touching the other wire. So a resistor connecting to another resistor. Yeah. So this is not a graph. That's the question. Yeah. So again, for this kind of system, we never draw graph. Okay, so this is not necessarily a circuit diagram anymore. This is sort of a circuit model of the power flow, right? So we're sort of very far away from the actual circuit. Okay, good, good. Any other questions about this? Yes, they're connecting a series of flows, what do you think, right? So this are connecting series. Right? Yeah, this flows. Yeah. Yeah, so exactly like current, exactly like current. This power flows exactly like current. Currents in series through resistors will be the same current. Yeah. Okay. Good. Right, so this is 0.2 over that. So this one is the other thing. 400. You compute this, you get 160, you get 240. Okay, so you do this, you can compute the flow along each path. So this is not very difficult. Right? So from here, you can write, if you want to send 400, send dqy. So this you get 240 one way and 160 one other way. So you get 240. So good. This is how the power will flow if you just sort of naively or just straightforwardly send 400. Injected 400 and took out 400 on the other end. Okay. The trouble here is now if you, but all these things have capacity. So now we can look at the capacity. We can observe that this 160 is higher than the capacity of those two branches. Okay, so if you observe this, this says that you have these two capacities. Okay? It turns out this 160 is too much. So it exceeds the capacity these two branches can carry. Okay? So once this exceeds the capacity, that means you cannot support the solution. Okay? Because the fact that you have a transmission network, you cannot support the solution. So that means that because you have transmission lines, you cannot always get the cheapest generator you want. Okay, so be the cheapest generator, you want to buy all your power from there. Well, sometimes what's stopping you is the fact that power flows. Okay, you cannot You cannot influence this. Okay? And another thing to observe is it doesn't matter if you increase the capacity of this line. Okay? This doesn't help you. Right? If you say, I want some more power from B to 1, the point is not to increase this capacity. This is not at capacity anyway. You can make this infinite capacity. You're still limited by lines that are sort of far away from you. Okay, so this is again the difference between, say, power and traffic, right? So you want to say, I want to more cars to go from Seattle to Tacoma. You increase the road capacity in Seattle and Tacoma. This is saying that it doesn't matter. What limiting you is points far away from you. It's not connected to, it doesn't, not directly connect to, it's not directly in between you guys, but still, what's limiting you is other capacities in the network. Okay, so this is another, because of the physics of power flow, there's another fact that you have to think about. Okay, so when, let's say, when you want to send more power, if you have to upgrade the line, you basically have to pay somewhere far away. Right? Both of you have to pay this guy, increase capacity. Okay, so that's why the economics of power flow can get a little bit counterintuitive. Okay, you often have to spend money seemingly to part of the system that's not directly related to you, but that's just a way it is. Okay. All right. So, any questions about this example? Okay. Yes. 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 Mhm. Right. Okay. Good. Right. Good. So that's the question is, if you increase capacity, will you increase reactance? Most likely no. So when you increase capacity, reactance goes down. The most typical case is you build a parallel line. Right. You just build some line in parallel to it. So when things are in parallel, the total reactance go down. Right. It's 1 over the reciprocal. So that goes down. The second thing that's more subtle, this capacity is not always a physical characteristic of the line. This capacity is often defined because of stability concerns, not thermal limitation. A lot of times has nothing to do with thermal limitation. A lot of times this is a stability limitation of the line. So in Pacific Northwest, this typically comes because of stability. Why that is, sort of is way beyond scope of this class. But often it's not that this is directly related to reactance. You can do other things with it. Right? So, for example, if some of you have heard of sort of DC transmission lines or DC power lines, the reason to have a DC power line is not capacity. That's more because stability. Right? But that's a much more subtle point in this class. But in this class, just remember that once there's some flow on some line, there's flows on other lines. And they have to sum up to something, right? So all this has to add up. Okay. Any other questions about this example? Good. Yeah. Mm-hmm. Both directions, yes. And they cancel, actually. They cancel. Flows on both directions cancel. Right. So flow, this is algebraic number. You can add and subtract. And the way we solve this problem is exactly that. We'll send some power here, it'll cancel that regard. So that's how this works. Right? So flows cancel. Flows cancel. Yes. And that's how all this, right? So see, basically you're looking at this, okay, this is the cheapest guy. I need to buy, I want to buy from this guy, let's say I can't. Maybe I need to buy from this guy. So if you send power here, actually there's some power flowing back this way. And that will cancel the power coming here. Okay, so power can cancel. So really think of power as current in all these things, right? So current can cancel. You can send current in both directions. Current can be positive and negative. Power similar. There's a direction to power flow. And positive and negative power adds up. It could cancel. Okay, so all the things can happen. All right, good. So any other questions? So we'll see a lot more examples. Okay, so let's take our break. Let's take a 5-minute break. Then we'll look at a lot more examples, like flows the other way and different how do you add flows and subtract. Back to this, right? So this is flowing from B to Y. You get this flow. So also from the notation B to Y. Why is this called B to Y? Because that's what your book wants to use. For some reason, the book just uses this shorthand for notes, right? So we're following that convention. Then so you have flows that may be right? So that may be violate the constraints. So now what you do is you can again, let's say I try to send power this way backwards. Okay, so what happens is if Y wants to buy from B, what saves you is, let's say now D try to sell to Z, and then you try to cancel the flows out. The flows actually cancel. Okay, so flows are now cars, for example, right? Cars don't cancel, car flows cancel. There's again, this really occurred. So now it's really occurred that cancel. Okay, so the counterintuitive thing is, let's say B to Y, they're sort of too expensive and I can't sell that much. The way that saves you is you want to reuse this path in the other direction, and then have flows that cancels the original flow. And then everything will be under the limit. So for example, our prices now becomes more complicated. I will do later this week. The prices will be a mixture of all the generators. So it's no longer you pick the most expensive generator that's being used. Now you have to think about how is the power redistributed. There'll be a linear combination of the different prices at different generators. Okay, so the exact ways of linear combination is determined by the reactance, basically, in your network. Okay, so if you look at this one, as you say, I want to send some flow backwards, what you do is you can say, okay, let's send some flow from B to Z. Okay, so let's try to send flow that way. So let's try to send a reverse flow. So let's try to flow 200 megawatt from B to Z. Okay, so we're gonna send back this way. And then your flow, so this F3, this backflow will be 0.2 over 0.2 plus 0.3 times 200. This is 80. The other flow will be 0.3, 120 megawatt. And then what you do is now you just add all the flows, actually. But the actual flow along these is you add the flows that are going this way and going this way. Okay, they will cancel. You add the two flows here, you add the two flows here. So these are the algebraic notations you can do here. Okay, so if you look at the flow as from 1 to 2, right? So at the end, what kind of flow do you get? As you have one flow going this way, F1. You have another flow going backwards, F3. So you have F1 minus F3. Right? So exactly that flows can add, they can cancel. So this is 160 minus 80. Right? Flows will cancel. You have F13. This is F2 minus F4. This is 240 minus 120. This is 120 megawatt. And similarly for F23. Okay, so all of these basically, you have flow again. There is a direction to the flow, and the flows will. There is a direction, and you can't add and subtract flow. Okay, this is again exactly like current. So electricity flow is not like traffic. It's not like water, but you cannot add up water from both directions, get less water, for example. So really, this is not the physically. This is not a commodity that's flowing. It's not a commodity. This is again something you can add and subtract. Okay. All right. So this is your power flows. And the idea is sort of power flow goes all around the node, right? So there's still linearly, these are all linear. What is the ratio of reactances? So there's linear combination of the flows, but you do need to do some algebra to get what the flow is. Okay? So here, all this is without loss. Look at add subtract. There's a loss, a little bit more complicated because you have two ends flowing both ways. There's a loss. The loss cannot be negative, right? So you have to sort of count the loss twice. That's a little bit more complicated, but we're not doing losses here. So here for lossless flows, where resistance is zero, the lines are inductive, you can add and cancel. You can cancel flows. Right? So the idea is basically whenever you have all this kind of path, it's a bit complicated, sort of very complicated, because you can have sort of a lot of physical transmission. Sort of complicated. It's not complicated, but it's a superposition of many. So at the end of the day, if you measure sort of the power sent as superposition of many things, and decentralized trading can be complicated. It's difficult to do in practice. Okay, so that's what the sort of transmission rights is. So remember last class we talked about bilateral trading. Okay, you just come to agreement with some other generator and the load come to agreement, and they say we'll send power. Well, if you come to that sort of agreement, sometimes depends on whether other people have come to this agreement or not, right? So again, in this example, if the only two people in agreement is B and Y, that's actually not possible, right? So there's spending too much power along this line. However, if there's also agreement going from D to Z, suddenly both agreements are possible, right? So that's where the complication comes from, right? You would think, why not have a completely decentralized market where sellers and buyers can just come to their own agreement, and you can take sort of the market system operator out of the market. The reason is that because of the physical power flow, someone needs to do this subtraction, addition and subtraction at the end. And because this feasibility constraints is actually very difficult to implement this sort of completely decentralized bilateral trading. Right? Because the sort of parties don't know what else is going on. And whether they're successful or not actually depends on, very hard to enforce. Turns out it's very hard in practice to enforce, right? So, and what can happen is you can have sort of a lot of market power. What can have a lot of market power is what could happen is, let's say I'm a generator. Okay, I'm a generator here. So how can I exercise market power is the following. This generator can buy some capacity on the line. The generator says, okay, I want to reserve some capacity for me. I'm not going to tell the market what I'm going to do with it. I'm going to buy some capacity. And then what does the generator do? The generator buys some capacity. How does this generator exercise this market power? This is a common game that people can do. And so let's say I'm a generator. I build a generator here. And now go and say I buy some capacity on it. How does that help me? Because there's no load on this side. Right? So why would you buy some capacity in this case? Right. So what you want to do is basically squeeze this two out of this. Right. So let's say you have two very cheap generators here. The load will want to buy from this generator. So from a social welfare point of view, what you want to have is if this generator wants to compete, it should have a lower cost, right? So lower cost for everybody, have a lower cost, then you can compete with the load, the total cost reduces, everybody's happy. What actually happens is I build a generator, I have a very high cost. What do? Is I buy out this transmission right. So it doesn't matter where these people costs are, they cannot use this line. Now I can go to the low saying, well, you have no choice now. You have to buy from me. So I can make a lot of money. So this is where in a market where you have added assets, we have added generation. There's more stuff in the market, but the price can go up because of market power. Okay? And this is not uncommon for this to happen, not uncommon. So, okay, so if you're a generator, okay, so this is, and it's not clear whether this thing is legal or not, actually, right? Because you say, okay, everybody can buy transmission. I can go buy transmission, right? So we come to our own agreement. So I agree with whoever built the transmission line. I want to part of this line. If I squeeze out other generator from the market, sure, right? So, you're doing a smart thing, you can increase your own profit. Okay, so this means that there's very difficult issues with around market power and physical transmission. Okay, so transmission can lead to what happens is you want to bottlenecks. Right? So whether these are actually physically exist, you don't have enough transmission, or created artificially by some financial trick, but either way leads to a bottleneck, and this can lead to market power. Whenever you have a constraint, the market power happens when there are constraints in the system. So the question is, can you create your own constraint? If you can do this, then you can win, right? So this is bottlenecks, and you have market power. So market power, basically, this is you're doing something that's decreasing the social welfare, right? So you're not, everybody's not getting the lowest price, right? You're basically charging people high prices. And we don't quite know how to avoid this, actually. This is not trivial to avoid. It's not trivial because if you limit too much, essentially it becomes a government monopoly. And we spend a lot of effort not to be government monopolies for electricity markets. If you don't limit anything, then this will happen. For example, this has happened in the United States many, many times. But where do you think this kind of thing happens the most in the US? There's a very, where people do this. Not Hawaii, not Hawaii. No, I think of something where it's geographically quite constrained in the continental US. New York City, this happens all the time. Manhattan. Okay, so what happens is there's just not that many space to build transmission line into Manhattan. Okay, and what you do is if you can buy out those rights, then you can charge anything you want in New York City. However, build a power plant there and say I want to charge arbitrarily high. I just make sure I buy out all the transmission rights. Okay, so somebody try this. I think one of the big. I think Morgan Stanley tried this once. Got fined about $500 million for doing this. That did not deter people. Then a year later, people tried this again with a storage unit. Okay, so what that said is, oh, generator not possible. Nobody said you have to be a generator. I put a storage there. People keep trying this, basically. And because, again, you can make for infinite money. Right? People will buy power at any price. If you're successful once, you essentially you can make as much money as you want. Okay, so this game goes on all the time. And, I don't know. I don't quite know whether this is legal or not. This is an open question we have. Yeah, you create a monopoly. It's not supposed to be a monopoly, but you can artificially create a monopoly. Right, so it's a question whether of you being smart or doing something wrong. And so this is a battle you fight with first. But so for example, Professor Daniel Kirschen spends quite a bit of his time thinking about this kind of problem. So how do you set up the market? That where on one hand you don't want to create a government monopoly, you don't want to regulate everything. On the other hand, how do you discourage market power from that? How do you not give people the ability to artificially create constraints to make themselves a monopoly. Okay? All right, so for now, what we'll do is after this point, we'll now consider market power. Because market power is a very difficult market power is sort of a difficult subject to consider. There's a lot of things that can happen. So from now on, what we will assume is people will not do this. Okay? There will be nobody that tries to play the market. Well, from now on, we'll assume that there is some centralized entity that will try to clear the market. Everybody is being truthful, right? So if they need to transmit, they'll transmit. If they need to generate power, they'll generate power. We'll see how do you fund basically the prices in the market, given that there are transmission limits. That's our goal. Okay, so yes, you can still have market power, or just sort of choose to ignore the fact that this can happen. Okay, so from now on, we'll assume that the players in the market are perfectly honest, and their goal is to maximize their profit without this kind of tricks. Okay, so they will obey what the central entity is trying to say. Okay, so what will happen is we'll assume things that are called. So assume things are called the perfectly efficient market. So we assume that efficient market. Okay, so nobody's trying to game it. Nobody was trying to game it. And the system operator basically has full knowledge. So this is the system operator knows everything. And it can optimally clear the market. And what it checks that there's no line flow violations in the system. And then, so if there's no congestion, then of course everybody gets one price. There's a unique market clearing price. If there are congestions, then we'll compute how the congestion is calculated. Okay, we'll do that calculation. Okay. So that's what we're trying to do. So I guess let's stop here today because I want to do the rest in one class. I want to stop in the middle. So one long calculation I'm going to try to do in one class. Okay, so let's stop here today. On Friday, we'll go through this one calculation. It's not terribly complicated. It's not that complicated. I'd rather do it once than stop in the middle. Okay. So the thing to remember is, if you want to really make big money, this is where it is. So I try to see if you can make this happen.